Okay, everybody, and welcome to the second part of Lecture 5. So let's begin by recalling what we did at the end of Part 1. I gave you this exercise where you had a representation, V rho, representation of a Lie algebra L, and we had a submodule U. It's just going to be a subspace of V such that when you act upon it by any element L, or rho of any element of L, to be more precise, you ended up back inside of U. And then we denoted the restricted representation like this, U, or I guess the pair to be precise. As you recall from the earlier lectures, whenever we have a subrepresentation, we can quotient it. So again, we define it in a natural way, and we denote this quotient representation as follows. Now, what I asked you to show was that if you take the associated bilinear form, the bilinear form associated to the representation, remember that whenever we have a representation, we have a bilinear form. If we have two elements, or x and y, what does the bilinear form do to these two elements? Well, you use rho, and you have rho of x, rho of y. These are now two elements of the endomorphism algebra of V. Hence, we can multiply them together because, I mean, with respect to a choice of basis, they're just matrices, so we can always multiply matrices. And whenever you have a matrix, you can consider its trace. So that brings you from the matrix into the field over which you're working. So that's what it was. That's what the associated bilinear form is. Rho of your matrix, rho of your element of the Lie algebra, rho of your element of the Lie algebra, multiply together, and then multiply together with respect to composition, and then take the trace of this map. Okay, you can think about with respect to a choice of basis or not with respect to a choice of basis. Of course, the trace is independent of any choice of basis. So what I asked you to do was to see that this bilinear form was actually orthogonal with respect to the decomposition of, so you should look at this. Of course, we have, when we have a subspace and we have the quotient space, as you know from basic linear algebra, we're going to have a decomposition like this. You should check that this is a decomposition of representations, but what the real part of the exercise was to show that the bilinear form associated to the representation actually decomposed with respect to this decomposition, that these two spaces were orthogonal. Okay, that anything inside here, if you took the bilinear pairing with anything inside here, you're going to get 0, which means that you're, as we've written here, your bilinear form decomposes into two parts. It decomposes into two separate subspaces where the bilinear form of one doesn't really talk to the bilinear form of the other. They're orthogonal. Okay, so that was the exercise, and hopefully you managed to work this out. If you didn't, send me an email and I can explain to you how to do it. Again, there's nothing really there except for working with the definitions and getting them clear in your head. So let's move on and now use this exercise, use this result, this orthogonal decomposition, to prove the following theorem. So remember, what is the point of this whole lecture 5? It's to find conditions, or to find a way of verifying that a Lie algebra is reductive or simple or semi-simple, sorry. Okay, because these conditions make sense in general sense, and we can make many statements about Lie algebras which have this form, be they reductive, simple, or semi-simple, but verifying them in the practice is not always immediate how to do this. So it's very useful to have a collection of tools, of tricks, basically, to test Lie algebra with, in order to be able to show that it is reductive or semi-simple or simple. Because basically with just the definition, trying to verify the conditions of the definition can be very difficult in practice. But that's why you need to rephrase the definition so that it becomes turn it into a form that's less useful theoretically, but more useful in the real world, which is to say the world where you're looking at examples. Okay, so enough philosophy. It's the statement of the theorem. Let L be a Lie algebra over a field K of characteristic 0, and let V sub rho be a finite dimensional representation of L, such that the bilinear form is non-degenerate. Okay, if we have this, then we can immediately conclude that our Lie algebra L is reductive. So it doesn't have to hold for all representations. You just have to find one representation, one finite dimensional representation, such that the associated bilinear form is non-degenerate, and then you can conclude that L is reductive. Of course, assuming that the field is of characteristic 0. Our assumptions about the nature of the field that we're working with come from the fact that our previous theorems, like Lie's theorem or Engel's theorem, were stated subject to an assumption on the nature of the field that we're working with. That's why they appear here. Or maybe I should say the fact they appear here is going to be an indication, a clue that in the proof we're going to use Lie's theorem. Okay, so first of all, we'd like to show that we haven't assumed here that the representation is irreducible. Okay, so we'd like to, it's always easier to work with representations that are irreducible, that can't be decomposed into subparts. So we'd like to show that we can reduce to the irreducible situation without any loss of generality. Okay, so let's assume that V is not irreducible. And this is precisely actually where the previous exercise comes into play. So let's assume that V is not irreducible, and let us try to produce from V an irreducible representation for which the bilinear form is non-degenerate. Okay, so let L be a sub-representation of V. If no such a non-trivial sub-representation, if no non-trivial sub-representation of V exists, well, then it's then it's irreducible, and then we're done. So assuming that this is not the case, let U be such a sub-representation. From the exercise above, we know that we can decompose the associated bilinear form into this orthogonal decomposition of the bilinear form with respect to the submodule U and the quotient module V over U. Now, because of orthogonality, we know that sigma V is non-degenerate if and only if both sigma U and sigma V over U are non-degenerate. Sorry, this should be R. Because it's an orthogonal decomposition. So in particular, we don't actually care about this so much. We care about the non-degeneracy of this guy. But both of them should be non-degenerate. For the if and only if. Again, it's not so important here. The important thing is that non-degeneracy of sigma sub V implies non-degeneracy of sigma sub U. So if the representation U is irreducible, then we're done, because we've produced, we want to show that the existence of a representation with a non-degenerate bilinear form implies the statement of the theorem. So we're trying to assume that it's not irreducible and then produce an irreducible from it. So if U is such an irreducible, then we're done. We can proceed. If it is irreducible, however, then we can just repeat the process. So we can pick another U prime that lives inside U. Then we quotient, we take the decomposition, we know the decomposition is orthogonal, and then we produce this U prime. And then we hope that U prime is irreducible. If it's not irreducible, then we continue one step more, and so on and so on. But basically, because V by assumption is finite dimensional, we'll eventually arrive at an irreducible representation. I mean, in the worst case scenario, remember that the dimension is going to drop every time because it's strict inclusion. It's a strict inclusion by our assumption that it's reducible. So you keep on going down by dimension every time. So I mean, in the worst case scenario, eventually you arrive at something which is one dimensional. And of course, this has to be irreducible. Okay. And from the exercise above, we see that each time you go down one step, the restriction of the bilinear form will again be non-degenerate. That's the point, because the decomposition is orthogonal. Therefore, we can assume without loss of generality that V rho is non-degenerate. Because to emphasize, we only need the existence of one representation, which is irreducible, to give us the statement of the lemma. So once we produce it from any starting point, it's okay. Anyway, maybe I've explained a little bit too much there, but everything you need is written. Now, it follows from the lemma preceding the theorem, that is preceding it in part 1 of the lecture, that for any k in the radical and y, the radical of L, and any y in the Lie algebra itself, and any v in the representation, which we're now assuming that loss of generality be irreducible, there will exist a lambda from the radical into k such that the commutator of x and y, or sorry, I should say the Lie bracket of x and y, which of course will be the commutator because the representation is always a Lie algebra map, is equal to this. And now we know that we should stop, pause for a second. So this here is actually contained inside V. V is a representation. Y is an element of L. It acts on V, produces another element inside V. And X then acts on this. But this is contained inside V, and we know that the radical, so we know that any element in the radical, such as X, will always act on any element of V of this form. So we can write this exactly the same here. It's even simpler on this side. X is in V. V is in V, so then X acts upon this, and it always acts as lambda because V is irreducible. Okay, that's why we went to the trouble in the previous slide of showing that we could assume without loss of generality that V was irreducible, because that's what we needed in order to apply this. It's the irreducibility of V that allows us to conclude that X acts just as a scalar. Okay, then that gives us this, gives us the lambda here, but of course we can bring this out because it's just a scalar, and then these two things are going to be exactly the same, so they cancel and it gives us 0. So that means that any such commutator, one of the elements is in the radical, will act on an arbitrary element V in our irreducible representation to give us 0. Okay, so this is sort of the main technical result we're going to use then to prove the theorem itself. Thus, from this, we see that the bilinear pair acts on any two elements, or a bilinear pair acts on an element of the Lie algebra times an element of the Lie algebra. This is an element of the Lie algebra. It's a Lie bracket, but it's still an element of the Lie algebra. So this makes sense. And if we see that, well, we just recall, the next step is recalling the definition of sigma. It's going to be the trace of the representation of this element times, sorry, this should be a composition here. It's composition of linear maps, or multiplication if you want to think about those matrices with respect to some particular choice of basis. So we take the product of the two of these, and then we take their trace. And it means that this is equal to 0. Why is it equal to 0? Well, because this element here acts on any element of V as 0, which is to say it's 0. So 0 by any element is going to be 0, and the trace of this is going to be 0. This is for and here. Okay. In other words, we see that, and there was no, we're taking an arbitrary element here of the radical, arbitrary element y and z of L. So it means that sigma of the Lie bracket of the radical of L by L is equal to 0. Okay. So to finish, we now use, so what have we used up to this point? We've used the fact that we have a representation. We didn't need to assume reducibility. We were able to get that for free. We assumed, let me just go back. We've concluded irreducibility, not completely for free. We've concluded it from finite dimensionality. then we've used that here. So let's just look at the statement of the theorem. Finite dimensionality and non-degeneracy. So that's the next thing we need to use. And this is precisely what we use here. Okay. So by assumption, it's non-degenerate. So that means that these guys have to be zero. Okay. Any element of this form, let's just go back up here. Any element of this form will pair with any element inside here to give you zero. So that means by non-degeneracy that any such element of these forms must be zero. What does that mean? Well, then we go back and we think about the definition of the center. Center are going to be those things whose Lie bracket with anything else is equal to zero. It's precisely what this is saying. So that means that the radical is contained inside in the center. But if we think back, the opposite inclusion is always true. The center was always contained in the radical. Remember, the radical was going to be the maximal solvable ideal, and which is to say any solvable ideal was contained inside there. The center was always solvable. It was trivially solvable because its commutator bracket or anything else was going to give you zero, so the solvability condition was satisfied immediately. Hence, the opposite inclusion is always true. But that means then in this case that we have an equality, which means that the radical is equal to the center. There is nothing in the radical that's not central. And what is this? Well, this is precisely the definition of reductivity. Hence, we can conclude that L is reductive, as claimed above. Okay. So I guess I said at the start that we're using Lie's theorem, and it may not be immediately obvious, but where is it? It's in this. We've used it here. The fact that the radical is operating with respect to a linear map. This theorem itself relies upon Lie's theorem, which needs our field to have characteristics here. Okay, so let's move on to another characterization, or another, it's not a characterization, but another tool to prove that a Lie algebra is reductive. But in this, we're going to do a bit more. Okay, so we're going to start off again with the field of characteristic zero. That's so that we can use Lie's theorem, which is so that we can use the same result about the radical acting on an irreducible representation as a scalar multiple of the identity, as we proved in the first part, and as we used in the previous theorem. So that's what's going on here. If we have this, then L, or Lie algebra, admitting a faithful irreducible representation is enough for it to be reductive. Okay. Let's worry about the rest of this in a while. Okay. So what we're saying is a faithful irreducible representation implies reductivity. Not that every representation should be faithful irreducible. If you can find one, then your Lie algebra is reductive. Okay. So it reduces the, no pun intended, it reduces the proof or the burden of proof that something is reductive down to finding a single faithful irreducible representation. Now contrast this to the previous theorem, where we didn't make any assumptions actually on the irreducible representation, despite this, except for the fact that it was finite dimensional. And we put most of our assumptions in the corresponding bilinear form. Here we don't mention the bilinear form. We just ask that it's faithful and irreducible. Okay. So let's start off use this condition. Let's use the faithfulness. What does faithfulness allow us to do? Why do we assume it? Because if you assume something in a theorem, the reason you assume it is because it gives you tools, because it allows you to actually do something. And what do we use faithful for? Well, we use it here in this first line. So since the representation is faithful, which is to say rho, what's the definition of faithful? The definition of faithful is that rho is a map, it's an injective map. It's a map that has no kernel. That allows us to identify L with its image inside in GL of V. in the Lie algebra of linear automorphisms, or linear maps, linear maps on V. Okay. So we can basically, if we prove the result about the image of L inside in GL of V, then that's enough, because it's an isomorphism of Lie algebras, and any of the properties discussed above are going to be preserved under isomorphisms of Lie algebras. Good. So by the previous lemma, I guess that's probably badly phrased. I mean, it's the lemma proved in the end of the first part of lecture 5. The lemma that says whenever you have an irreducible representation, then the radical, or maximal solvable ideal, is going to act on the representation as a scalar multiple of the identity. Okay, and that's where this assumption comes in, the field of characteristic 0. Because it allows us once again to use this very, very useful lemma, which itself comes from Lie's theorem. Now, that means that the radical of L, identified again as contained inside in this algebra of linear operators, it has to be contained inside in the one-dimensional space spanned by the identity. Okay, because of this here. Repeating myself, every element of the radical acts as a scalar. Different scalars for different elements, that's fine. The relationship between different elements is linear, which is to say this is a linear map. But nonetheless, every element acts as a scalar multiple of the identity. And that means that the whole thing itself is contained inside here. But this is now true, we see, because the identity matrix is in the center. The identity matrix clearly commutes with everything else. It's Lie bracketed with everything else is 0. Hence, it lives inside in the center. And now, as we recalled in the proof of the previous theorem, the center, Z of L, is always contained inside in the radical. Because the center is a solvable ideal, it vacuously satisfies the condition, not vacuously, but it trivially satisfies conditions of a solvable ideal. This guy here, the radical, is going to be the sum of all the solvable ideals. Therefore, this is contained, Z is contained inside in the rad, giving us the opposite inclusion, allowing us to conclude that two things are the same. Which is to say, the radical is equal to the center, but that's precisely the definition of L being reductive. So great, that's it, we're done for this part. Okay, similar style of argument to the previous one, but just starting from different assumptions. So now let's move on here. It says that from these assumptions here, that not only can we conclude that L is reductive, but also that the dimension of the center is going to be less than or equal to 1. If it's less than 1, then it's going to be 0, then it's going to be trivial. The only element that trivially pairs, whose Lie bracket, or I guess if you think about it as identified with the representation, the only element which commutes, the only element of L that commutes with everything else is 0. That's one possibility, or it's one-dimensional. Okay, but if it is one-dimensional, then we've already shown at the radical that the radical is going to be contained inside a one-dimensional space, which is to say the one-dimensional space spanned by the identity. So if these two things are equal, then we know that the dimension of the center is at most 1. Okay, so in fact, this second part here is really just a consequence of this inclusion here. That's all that's going on. All right. So now we move on to the second part, which we've put an extra assumption there. And from this extra assumption, we want to reduce from our Lie algebra being reductive to the stronger condition of it being semi-simple. So assume that L is contained inside an L, where again, because it's a faithful representation, we've identified L with its image on a row inside GL of V. So if we assume that it's actually contained inside an SL of V, those linear operators which have got trivial trace, zero trace, if the radical were equal to zero, sorry, if the radical were non-zero, if the radical were zero, then we know that we would have semi-simple. Remember, that was a characterization of semi-simplicity. It's going to be that something was reductive if this was satisfied. But if in addition you asked that the two of these things were not only equal, but they were equal to zero, then that's what semi-simple was. So if the center of the radical is zero, then we've got semi-simplicity. Great. If the radical was not zero, okay, then it would have to be equal to the one-dimensional vector space spanned by the identity, because we previously showed that it was contained inside. All right. So this is a one-dimensional space. If it's contained inside there and it's non-zero, it has to be equal to everything. But what would this mean? Well, this would mean that the identity was contained inside in the radical. But the radical is contained inside an L. So maybe it would help to have an L inside here. And by assumption, L is contained inside an SL of V. But this is, of course, a contradiction, because if you take the trace of the identity is non-zero. The trace of the identity is equal to the dimension of V. That's a contradiction. So basically, we assumed this and we got a contradiction. Therefore, this can't be true. Therefore, the radical must be zero. Therefore, zero is equal to the radical is equal to Z of L. And this is an equivalent formulation of semi-simplicity, which means that we must conclude that L is semi-simple. Okay. So that's basically where we leave it. No, not quite yet. Sorry, I've forgotten about this slide. So in summary, just to recall what we had before, excuse me, this is a typo. That should of course be zero. So for zero characteristic, we can conclude that our Lie algebra is reductive from either of the following. That if we can conclude that it's reductive if we have a representation together with a non-degenerate trace, a non-degenerate bilinear form, I guess I should really say. Or alternatively, we have a faithful irreducible representation. Either of these, showing either of these two things is enough to conclude that it's reductive. And moreover, in the second case, if the representation rho satisfies this inclusion here, then we conclude that L is semi-simple. Okay, so some good ways to verify in practice reductivity or stronger condition of semi-simplicity. And let me leave as an example or an exercise. We'll do this in the exercise classes. Recall the definitions that we have: GL of K or U of N. This is over the complex numbers. This is a general field. Use the above results to show that these Lie algebras are reductive. And use the second to show that this algebra and this Lie algebra are semi-simple. Okay, so a good way to get a feeling for the conditions for the statement of those two theorems is to try to verify them on these elementary but extremely important examples of Lie algebras. Okay, so we leave it there. Thank you for your attention, and we'll see you in the next lecture.